So this is a paper we just put on arXiv. It's about branching processes that arise in connection with Graphon. And we did it while my co-authors, Anna Limbach and Keat, worked at the Czech Academy of Sciences. And since Keat moved to the Institute for Basic Science in Korea. Okay. So let me try to get this working. Okay. So here is what the talk will be about, condensed into 3 minutes. So you have multiple models of sparse random graphs. Okay, so I emphasize the word sparse here. One is the sparse R-range random graph. And I do mean the probability scales as 1/n. And the other is the uniform spanning tree, so a randomly chosen spanning tree, which of course, again, is a very sparse graph. And what we do with these models is that we describe when do these models yield similar distributions. And I will give you a specific example in a minute. So to this end, we do use the language of dense graph limits, which was developed by Lovas and co-authors circa 20 years ago, even though for the first half of the talk, you will not see any mention of that theory explicitly. It will be implicitly there all the time. So let's actually look at a specific example. So this is actually the second theorem. So now we are sort of 50 minutes ahead of time. The second main theorem in a very loosely formulated. Okay. So here are 3 examples of graphs, of what I would call dense graphs. So one of them is the complete graph on n vertices. The other is the complete balanced bipartite graph, so n-half, n-half. And the third one is a complete unbalanced bipartite graph. On this example, is 20% of the vertices end up in one color class and 80% of the vertices end up in the other color class. Okay. And in all these examples, n will be large and will go to infinity. Okay. And what you can do is you can look at the uniform spanning tree in each of them. So you are looking at this random object out of all spanning trees in the complete graph, or in the complete balanced bipartite graph, or in the complete unbalanced bipartite graph. You pick one spanning tree uniformly at random, and you are looking at a typical such, right? So you are looking at typical behavior of your random object. Okay. And it turns out that in these first 2 models, so in the complete graph and in the complete balanced bipartite graph, the uniform spanning trees are similar. And in the third example, the uniform spanning tree looks genuinely different. Okay, I will not define the similarity notion. It's what's called the Benjamin-Schramm topology. But one instance of this, which is very easy to describe, is the number of leaves. Okay, again, this is not an if and only if characterization of the similarity notion, but it turns out that if you look at the uniform spanning tree of the first, of the complete graph, the proportion of leaves is roughly 37%. It happens to be 1/e. Okay. And so is in the second example. Whereas you can do some calculations and you will find out that in the third example, in the unbalanced bipartite graph, the uniform spanning tree typically has around 63% of the vertices are leaves. Actually, the third example, you can you can't get this constant that easily, but there is a deterministic argument which shows that, you know, in any spanning tree, most of the vertices of the blob on the right end up as leaves. Okay. So what we do in this project is we try to explain why is it that the first two examples yield similar spanning trees, even whereas the third example yields a very different uniform spanning tree, right? Which may be a bit surprising because in some sense, the complete balanced bipartite graph is closer to the complete unbalanced bipartite graph than it is to the complete graph. But we give a characterization, as a matter of fact, of all the graphs or all asymptotic structures which give you uniform spanning tree, which behave similarly like in the case of the, say, complete balanced bipartite graph. Right? And we do it. There is the complete balanced bipartite graph, and the other two graphs are taken just for the sake of concreteness, but we have a general characterization. Okay, so here is the program. I will first recall some basic concepts from probability theory, Poisson distribution, and Golden-Watson branching processes. I will talk a little bit about Erdős-Rényi random graphs, in particular with this so-called giant component phenomenon. And I will introduce a generalization of these due to Bolobash, Jansson, and Riordan, and again talk about this giant component phenomenon in this more general setting. Okay, and at that moment I will be ready to state our first theorem, first main theorem, which is about random objects coming like from these Bolobash, Jansson, Riordan inhomogeneous random graphs. Okay, so branching processes related to this Bolobash, Jansson, Riordan inhomogeneous random graphs. That theorem uses the notion of fractional isomorphism. That's a notion which has been well studied in finite graphs. There is a recent extension to graphons, which we use in that characterization. And sorry. And then I will talk a little bit about uniform spanning trees, which is a different probabilistic model. And I will state the main theorem, which I have hinted already. Okay, so very quick recap. The Poisson distribution is a distribution on non-negative integers. It's parameterized by a single positive real, I will call it lambda. Okay, and there is this formula which is not important for me at all. But what is important is that the Poisson distribution is a limit of binomials. Okay, so what I have on this picture on the right, on the plot on the right, is a Poisson distribution with parameter 3.5, let's say. Okay, so there is a certain probability of, I guess, 4% that it attains value 0. There is a certain probability, maybe 11%, that it attains value 1. The values 3 and 4 are the most likely. They are closest to my parameter lambda equals 3.5. That parameter actually happens to be the expectation, the expected value of your Poisson lambda valued real random variable. And then there is this tail. So if you want to get this, if you want to get approximately this distribution, what you can do, so Poisson 3.5, what you can do, you can toss 10 many times a biased coin with success probability 0.35. Okay, and you can count the successes. If you want to do it more precisely, if you want to generate your Poisson 3.5 more precisely, then you can toss another coin 100 many times, so many more times. But now you you sparsify the success accordingly. So now, instead of success set to 35%, you set it to 3.5%, right? Because 100 times 3.5% is, our lambda equals 3.5. Okay, so that's what I mean, that Poisson is the limit of binomials. The number of trials is n, and the success probability is lambda over n. Okay, this is something we will use throughout. Okay, and I quickly recall this notion of Galton-Watson branching processes. Okay, so what that is, it's a random tree, a random rooted tree. And what you have, it's a very natural model of, say, reproduction. You have the root, and the root has a random number of children. So, okay, so the root for me, the root is always denoted with a square, and the other vertices are circles. Okay, the root has a random number of children, and each of these children has a random number of children of its own. Okay, and what I will be using throughout the talk is Galton-Watson branching processes in the Poissonian case, where I have a single real parameter, lambda, again, let's use 3.5, and the number of children the root has is Poisson with parameter lambda 3.5. So, for example, this is quite a plausible scenario. The root has 3 children, and one of these children has 4 children of its own. One of the children has 2 children of its own, and the third child has 4 children of its own, and so on. So this is something that may easily happen. Okay, and I will use this GWB as an abbreviation for Galton-Watson branching with parameter lambda to denote this random object, again in the Poissonian case. So this is a very well studied classical subject in probability theory. In particular, what is known is that when lambda is at most 1, the Galton-Watson branching process with parameter lambda goes extinct almost surely, goes extinct with probability 1. Whereas with lambda equals 0, so you don't get the complete opposite. So you don't get the Galton-Watson branching process survives. So what it means, survive and go extinct. That means that the tree is either in the survival regime, it's infinite, it has infinite depth. In the extinct case, it's a finite tree, right? The Galton-Watson branching survives with probability which is positive, but it's never 1. Okay, it can't be 1 because, for example, you can die immediately. The root can have 0 children, so you die immediately with positive probability already in the first generation. Okay, and this survival probability is known. That's known how to compute, or maybe there is not an explicit formula for it, but there is an equation which it has to satisfy. So it's a well-known quantity. Again, which I will denote as S lambda. Okay, so S lambda is strictly, for every lambda is strictly between 0 and 1, and as lambda goes to infinity, it goes to 1, because somehow it's very unlikely in that case that you would go extinct, because most of the vertices will have many children of their own. Okay. So I will very quickly recall this notion of Erdős-Renyi random graphs. I will denote them G and P. So you have this fixed vertex set 1 up to n, and each pair, so n is an integer, and each pair forms an edge with probability P. Okay, so P is a number between 0 and 1. And, most of random, so you study asymptotic properties where when n goes to infinity, it turns out that when P is a constant, most of the questions that might come, most of the graph theoretic questions that would come to your mind are actually very easy. So what is more interesting usually is to look what happens when P goes to 0 as n goes to infinity at various ranges. So, depending on the particular problem, whether you are looking at Hamiltonicity, connectivity, deviations of the number of triangles. So there are, various ranges of interest. But I will be looking at the sparsest reasonable regime, which is P is a constant over n, maybe 10 over n, maybe 3.5 over n. And that is usually the hardest regime to understand, for example, because you don't have concentration. Okay, so random graph theory is a very mature field by now. Many books have been written about it. So I don't think it's fair when you have such a mature and substantial theory. I don't think it's fair to say that there is a single most important theorem. But if there were, then it would be the phase transition theorem, which surprisingly enough appeared already in one of these first papers by Erdős and Renyi in 1959. Okay, so let me recall this phase transition. So we are looking at the sparsest reasonable regime of Erdős-Renyi random graph. So we are looking at Gn, and the edge probability is C over n. Okay, and now there is a very substantial change in the structure of the graph as C changes as it passes the barrier 1. Okay, in particular, when you fix C 0.99, then the largest component of Gn 0.99 over n is only of logarithmic order. Okay, but if you look at Gn 1.01 over n, then the largest component is already of linear order. Okay, so there is a constant depending on n, so that I denote it here as SC times, so that the order of the largest component is roughly SC times n. Okay. By the way, the letter I'm using is the same as the letter I used for the survival probability of Galton-Watson branching process, because actually it is the same constant. Okay, and we will see that in a minute. Okay. So these early proofs, so this was proven in 1959. There were subsequent developments where people were looking at something called window around criticality and so on. So people were sort of improving the proof of Erdős-Trényi, but all of them used in some sense the same technique, which was enumerative, so a fairly natural, but a very technical, very tedious technique. And then in 1990, Karp came and said, oh, let's use Galton-Watson branching processes. Okay, and that has been used since. It's a much more convenient technique, much more intuitive. Okay, so actually, let me again. This is a very standard technique, but for those of you who haven't seen it, let me try to recall it. By this example, we would want to understand the component structure. So, for example, the size of the giant component, right, the largest component, in Gn, 3.5 over n. There's nothing specific about 3.5, but I'm now in the supercritical regime. This theorem of Erdős-Trényi tells me that there is a single linear-sized component. They can actually predict the leading constant, and the other components are of logarithmic order. Okay. And I would like to recover that result, or at least partially recover. Okay. So, and for that you ask this question: what is the neighborhood structure of vertex 1? Okay, why 1? Well, there is no reason, right? So 1 is as good as any other vertex. You have complete symmetry in the Erdős-Trényi random graph. Okay, so how does the neighborhood look like? Well, number 1 has any number of neighbors between 0 and n-1, right? If it's connected to everyone else, then the degree is n-1. Okay, so there are these n-1 potential edges which may facilitate neighbors to number 1. So you reveal them, you expose them. So like I did on this picture. Of course, it's a very sparse setting, so most of these pairs, 1 versus something else, form non-edges. On this picture, 29 and 25 and 49 are neighbors of 1. So actually, what is the distribution of the number of neighbors? Well, I had these n-1 potential connections, potential neighbors. So that's like the number of trials I'm doing. And the success of any particular one becoming a neighbor was 3.5 over n. Okay, so I have the degree is binomially distributed with parameters n-1, 3.5 over n. Okay. Okay, so let's actually, that was the first neighborhood. So what's the second neighborhood? Okay, so I should reveal the neighborhood of 25, and I should reveal the neighborhood of 49. So let's do 25 first because it comes first. Okay. So let's just discard the two vertices which I have already explored, which were vertex 1 and vertex 49. And for the remaining for the remaining ones, and there are n-3 many of them, let me again reveal the pairs, right? 25 versus everything, all the rest. Okay, in this case, I see maybe there was a single edge to 82 and so on. Okay. So what there is a simple argument that with high probability, it's only interesting to fan out. There are no edges inside. Why? Because, between each particular pair of edges, a pair of vertices, there is a negligible probability of inserting that edge. So we really end up with a tree structure And that tree structure is asymptotically, when n is large, is the structure of the Galton-Watson branching process with parameter 3.5. Why? Let's actually look at that again. Well, the neighborhood of 1, the neighborhood of the root, was binomially distributed with parameters n-1 and 3.5 over n, which is almost the same as binomially distributed with parameter n, 3.5 over n, which, as we know, is in the limit Poisson. So the root had Poisson many children, and any of them had, okay, so this case, binomially n-3, 3.5. Well, binomial n-3, I can, I can add or decrease any constant in the first parameter of the binomial. It doesn't really matter. So this is again approximated by Poisson. So each child has in the tree has a Poisson 3.5 many children of its own. Okay, which is really the definition of Galton-Watson branching process. Okay. So the neighborhood structure of vertex 1 is like the Galton-Watson branching process with parameter 3.5, at least when you are looking at the, into constant depth, let's say. So what's the size of the giant component then? Well, let me just reformulate it in the most, in a trivial way, but it's a very useful way. The size of, okay, so this is a trivial reformulation. The size of the giant component is just the number of vertices in a giant component. Okay. And that's n times the probability that vertex number 1 ends up in the giant component, right? Because vertex number 1 is as good as any other vertex. And what we saw is that vertex number 1, it branches out of the neighborhood structure, at least on reasonable scales, is like that of the Galton-Watson branching process 3.5. So to be in the giant component, you need not to die out too soon. And we call that quantity on the slide with Galton-Watson branching process is SC. So it's SC times N. Okay. And that, you need to do some more technical calculations, but this is the end of the proof. So this really proves the theorem of Erdős-Renyi. Okay, so that was the Erdős-Renyi random graph, which has been studied extensively since the 50s. Books have been written about it, thousands of papers. And now, you are explaining this to a friend at a party, at a sociologist friend, and they ask you, well, what is this all good for? And somehow to give a motivation, you say, oh, this is like it's a model of randomly forming friendships. You have a population, say on the planet, you have a population and people form friendships randomly, and then you can study how, what is the largest clique where, each two of them are friends and so on. Right? And what that sociologist would tell you is that this is, of course, nonsense. So you can't, the probabilities are not the same for people over, or pairs of people over the Earth, right? Typically, for example, people who live geographically close to each other will have a much bigger probability of forming a friendship. People of similar age or similar mother tongue and so on. Okay, so this is the model, now we are getting to a model which was introduced by Bolobash, Jansson, Riordan in 2005. On the right, you can see the corresponding issue of random structures and algorithms, where this first paper of theirs was published. I gave it here because actually you can notice that the whole issue is just, I mean, there is a two-page introduction by the editors, but then the whole issue is just this one paper of theirs. Right? So they introduced the model, which I will give here in a somewhat simplified, like I will not give you the full generality of their model, but for most purposes, I will give you a model which is sufficiently general. And actually what they do in the paper is they study exactly the giant component question in that model. Okay, so the model is a generalization of the sparse R-Renyi random graph model. The sparse R-Renyi random graph model was, we would write Gn and then a constant over n. Okay, so there was a single real parameter. Now the model is much more complex because I write Gn w over n. So there is a single parameter. Okay, there is n as the number of vertices, but other than that, there is a single parameter called w, but it's a much richer parameter because actually it's a parameter which is a function. Okay, so it's a function defined on the unit square, and it's a bounded function. So here I wrote it's a function to 0 to 999. Of course, that's an arbitrary number. It's just an L infinity function, let's say. Some of these things work even for L1 functions. I will not be going into that. And it's symmetric, okay, meaning for every x and y, wxy equals wyx. Okay. So here is an example. Here is an example of a graphon, right? For the purpose of this talk, and actually I do it in general, I draw graphons with the same orientation of the Euclidean plane as you draw matrices, right? Usually in the Euclidean plane, the x-axis goes from left to right and the y-axis goes from bottom up. But actually for matrices, the first axis goes from left to right and the second dimension goes from top to bottom, right? So I'm using that convention here. Okay, so in particular, the main diagonal goes from the top left to bottom right. Okay, and there are various shades of, so the way I'm depicting it is that various shades of gray represent these various values between 0 and 999. Okay, and you have continuum many values. Okay. So how do you, there was this very simple procedure of generating R-Renyi random graph. So I now need to define the model. So I need to tell you, how do you create the graph, the random graph Gn, w over n? Okay. And so here is how. Like in the previous example, the vertex set is deterministic. So the vertices are just 1 to n. Okay. And then, okay. You throw in word elements x1 up to xn into the unit interval at random. So this is what I did here. I have a copy. The x-axis is a copy of the unit interval. And I put these points x1, x2, x3, x4, x5, x6 at random, right? And once I did it, I could I could reflect, I could mirror it on the y-axis, the same points I mirrored on the y-axis as well. Okay? And these points now are representing, they are geometric representation of the vertices of my graph. Okay? And now I need to decide for each pair of vertices, I need to decide whether in this random graph model, whether it forms an edge or not. Okay, so let's do it. Let's do it, for example, for the pair 1, 4, right? So I need to decide, I need to make a decision whether 1 and 4 form an edge or not. So to this end, I look at the point with whose x and y coordinates respectively are x1 and x4. Okay, I see a certain value there, and I insert an edge into the graph with probability wx1, x4 divided by n. Okay, so that's this sparsification. Okay, and by the way, you see that this only makes sense when n is at least 999, because, you know, when I say insert something with probability, then the number that follows must be a number in the interval 0, 1, which is guaranteed only in that case. But, you know, we are studying asymptotic properties, so we can wait until n is bigger than 999. That's not a problem. Okay, so that's the model, right? And again, okay, so here's another second example, 3 and 5. Okay, so I look at the, you know, pointed coordinates x3, x5, this one, and actually there I do know that with probability 1, I will not insert an edge, right? Because the value here at this position is 0. So the probability of insertion of an edge is 0. Okay. So we have the model, and the question Bolobasyan, Sonter, and Triordan studied was, what's the size of the giant component, if there is one? So, you know, Erdős and Renyi would tell us that in the classical random graph, you know, for some regimes, when C is less than 1, there is no giant component. When C is so all components are of logarithmic size, and when C is bigger than 1, then there is a component of a much bigger one of linear size. Okay. So, okay, so we again need to understand this question, what's the neighborhood structure of vertex number 1, right? And in G and 3.5 over n, we knew that the answer was, well, it's the Galton-Watson branching process with parameter whose offspring distribution is Poisson 3.5. Okay, so let's say that in this inhomogeneous setting, when we have a kernel W, the neighborhood structure of vertex 1 is Galton-Watson branching with parameter W. Okay, so I mean, it's definitely a correct answer, except we don't know what this Galton-Watson branching with parameter W is. So let's do that. Okay, so now I'm defining, okay, so this is now a new definition, Galton-Watson branching which is parameterized not by a number, but by a kernel, by a two variable function. And this is a much less standard definition. So, you know, this is not a standard object in probability theory. So this is what you do. You know it's a branching process, so there should be a root. Okay, and now all the root and all the other vertices in your random tree will have types. So this is a new feature. Okay, and what you do is you generate a random number in the interval 0, 1. Here I happen to have generated 0.42. Okay, which is, and I put, you know, the pointer, the x1 is at position 0.42. Okay, So that's how you generate, that's a one random step, you're generating the type of the vertex. Okay. And the intuition is that you look at what would be called a degree. So you take this one-dimensional slice of the kernel and you integrate this one-dimensional slice. Okay. And somehow, if this integral is big, then the root, you expect the root to have many children in expectation. And if it doesn't, then, yeah. Then if it has small degree, then it would have few children in expectation. Okay. So you generate, according to this degree of this vertex, you generate Poisson many children. Parameter is the degree, and you do it in some, in a process which is called Poisson point process. Okay, which I will not explain. I don't have time for that. But it's a fairly intuitive. First, you generate, let's say, the number of children you want to have. It should be Poisson with parameter degree, and then these children, they tend to go to places where there is higher density on this slice. Okay. So in this example, I generated 3 children, and it's not only the number 3, but actually, the first child its y coordinate was 0.12. The second child, its y coordinate was 0.43. The third child, its y coordinate was 0.53. Okay. And then you repeat the same process. You reflect this to the x coordinate. Right? So here is, the point at position 0.12, and you repeat the process. Okay, for these children. So, for example, now on this picture, the red child will have 4 children of its own. Again, they will have specific types. The green child has 1 child, and the yellow child has no children of its own, which is actually, yeah, fairly plausible, because the yellow one was born at a place where on the slice function, the values are not that great. Okay, so this is the summary of the process. Okay. Now, this is basically what the main theorem of Bolobash-Samson-Riordan says. Let SW, okay, so again, we used to have S with a single real, right? But now we are feeding in a kernel. Let SW be the probability of the survival of this inhomogeneous Galton-Watson branching process with parameter W. Then the largest component in GW over N in this inhomogeneous random graph is of linear size, and the leading constant is SW. That's their theorem. Okay. So here are 3 examples, 3 kernels. I could have the constant 0.8 kernel. I could have the constant 3.5 kernel. I could have this sort of bipartite structure, right? It's a balanced bipartite structure where across I have intensity of 7. And what I have the last example, that's an unbalanced bipartite structure where the ratio or the sizes of the 2 color classes are 0.25 and 0.75 respectively. Right? Okay, so we have 4 kernels, and let's run the Galton-Watson. Let me show you what the Galton-Watson branching is in these 4 cases. Okay, just examples. Okay, so what is quite likely to happen in the first example is that you will actually die out pretty soon. Okay, so maybe in this example, the root was born. Okay, so all the roots, they happen to have label 0.42. Or maybe I generate just one root and went from there. Okay, and this root should have Poisson 0.8 many children, so maybe it had one child, why not? Okay, and this child had a particular type, which is completely irrelevant here. So note that the types are irrelevant in this example, because actually all the vertices, all the paths look the same, right? And this child had no children, which is quite likely to, quite possible to happen when you have Poisson 0.8 many children. Okay, so the second example, the root has Poisson, no matter where it was, it had Poisson 3.5 many children. These children have actually, the labels of these are uniformly distributed, and each of them has, again, Poisson 3.5 many children of its own. Again, the labels are uniform, the types are uniformly distributed. Okay, so the third example is a bit more interesting. So what happens if you take any vertex, any element on the x-axis, and you look at the slice function, and at this slice, as we were doing, and so you are trying to compute the degree of that vertex, then on half of the time you are integrating 0, and half of the time you are integrating 7, meaning every vertex. Okay, it's true even for this part of for the right half of the interval, except that the order of integration is it goes the other way around. So first you are integrating 7, and then you are integrating 0, but still the total is 3.5, right? So what happens is that the children of each vertex has, again, Poisson 3.5 many children, but the children are of the opposite type as was their parent. Okay, and by the opposite type, I mean if the parent was in the first half interval, so its type was between 0 and 0.5, then the children will be of their type will be in the second half interval, and vice versa, right? So you started with the root whose type is less than 0.5, and all the children have types which are more than 0.5, and all the grandchildren have types which are less than 0.5. Okay, so this will necessarily happen, but other than that, the law, the distribution of this process, modulo the labels, is exactly the same as in the second example. The third and the second example yield different labels, but they are, as unlabeled random trees, they give you the same distribution. Okay, this is really important for what will come later. Okay, we'll just say that because the second and the third kernel are fractionally isomorphic, whatever that means. Okay. So in the third example, okay, so I have the root has type 0.42, which is somewhere in this part. Okay, meaning if you look at this integral, the integral is rather small because you are most of the time integrating 0, and here you are integrating 4. Okay, so what you have is the root will probably have a small number of children, but those children, again, you have this alternation. Those children will be of a type which is necessarily smaller than 0.25. And if you look at this integral, then that one is big. That integral is 3. So the child is going to have, okay, likely to have many children. Okay, so there was a little break, but let's get going. So there were these processes which we had for these 4 examples. And let me just, instead of these specific pictures, let me write down what we arrived to. So in the case of the complete constant 0.8 kernel, what we arrived to was an ordinary Galton-Watson branching process corresponding to constant 0.8. Obviously, the same with a different constant for the constant 3.5. What we saw is the third example. Again, when we forget the labeling, also yields just Poisson Galton-Watson branching process with parameter 3.5. Actually, more generally, whenever you have a kernel where every degree is 3.5, you do get the same GWB 3.5. Okay? And the last example is a bit more complicated because depending on where you sample the root, whether you sample it from the sort of first part of measure 0.25 or the second part, which is of measure 0.75, you arrive to either Galton-Watson branching, which in even levels has branching parameter 3 and in odd levels has branching parameter 1, or you swap the parity, right? Okay. So now we have all the ingredients, or actually half of the ingredients, to state our first main theorem. Let me recall that. Sorry, there was a technical issue, but that's now back. Let me recall that we have 2 main theorems. One, so far I've been doing this Bolobash-Jansson-Riordan branching processes. And here the main theorem is that for 2 kernels U and W, the following are equivalent. This inhomogeneous branching process of U and the inhomogeneous branching process of W yield the same distribution, again, as when viewed as rooted, possibly infinite, unlabeled trees. Okay, so that's one part of the equivalent, and this is equivalent to U and W being fractionally isomorphic. Okay, so that's the theorem. The problem is that we don't understand this notion of fractional isomorphism yet. So let me now introduce it. Okay. Then we can't understand the main theorem otherwise. So the main theorem is in characterizing when do 2 Galton-Watson branching, these inhomogeneous Galton-Watson branching processes yield the same distribution, or if you want to look at it with the lenses of finite random graphs in mind, you can think of it as when I generate these inhomogeneous random graphs from a kernel U or from a kernel W in the same way as Bolobash-Jansson-Riordan introduced it, when do I get random graphs with similar local structure? Okay. And the answer is if and only if the 2 kernels are fractionally isomorphic. So now fractional isomorphism in graphs. Okay, so now I'm first recalling the notion of fractional isomorphism in graphs, which is a well-established notion. Okay, that's the first step. And the second step is I will translate it, or rather I will recall how a recent paper of Grebik and Rocha translates that concept for kernels. Okay, but you know, so strictly speaking, we don't need the definition of fractional isomorphism for graphs, but it gives you the right intuition for kernels. Okay. So one of the magics, one of the beautiful things about fractional isomorphism for graphs is that there are multiple definitions, very different looking ones, which all turn to be equivalent. So I will mention them on a later slide. But what the definition I chose here is perhaps the most intuitive one, and it goes by the name of color refinement algorithm. Okay. And somehow the motivation behind this definition is, if you have the usual definition of isomorphism, so of ordinary isomorphism of graphs, then one trivial fact it implies, one trivial feature it implies, is that the two graphs in questions have the same degree sequence, and you can iterate this fact. Okay, so this is the idea behind the definition of fractional or one of the definitions of fractional isomorphisms. So I have these two graphs G and H, and I will run this color refinement algorithm and determine whether I declare G and H to be fractionally isomorphic. Okay, so I will show what I do only on graph G. Of course, you do the same for graph H later on. Okay. So the first step is you partition the vertex set of graph G according to the degree. So, you know, there are some isolated vertices, and I will call those V0. There are some vertices which are of degree 1. I will call that V1. There are some vertices of degree 2. I will call that V2, and so on. Okay. So obviously, you know, I partition the vertex set into finitely many sets, at least if I care about the non-empty ones. So, okay. I could do that for H as well, and I would say that G and H are not fractionally isomorphic if some pairs of the corresponding sets don't have the same cardinality. So if V7 of G doesn't have the same cardinality, if the number of vertices of degree 7 in G is not the same as the number of vertices in H, then for sure they are not fractionally isomorphic. So that's a necessary condition, but it's not a sufficient one. Okay, because you now iterate it, right? So it's like if you and I have the same number of friends, okay, so then in some sense we are similar, but then you could say, okay, but my 7 friends, you know, each of them has 3 friends of their own, whereas your 7 friends, you know, 2 of them has no other friends, and 5 of them have, you know, 10 more friends, right? So maybe our friendships are, you know, there are differences in our friendships. So that's this sort of iteration is what we do, right? In particular, what I did is I'm now looking at this set V4, right? So the set of vertices of degree 4, okay, and I pick this subset, okay, so I'm, you know, notationally it's going, whatever notation you are going to pick, it will end up as, you know, awful, but I'm writing this V4, V21, V41, V72 means the vertices of degree 4, which, you know, of those 4 neighbors, 1 goes into V2, 1 goes into V1, and the remaining 2, right, go into V7. Okay? So, you know, you could refine this set V4 like this, again, into finitely, there are only finitely many meaningful types. Okay, and okay, again, you would do that for H. You would say, well, if you know this V4, V21, V41, V72 of H is of different cardinality than it is in G, then for sure they are not isomorphic. Okay, and now you iterate it even further. You can sort of look at your friendships of depth 3 and so on. Okay, and you declare G to be fractionally isomorphic to H if this, color refinement algorithm run on G and run on H produces the sequences or offsets of of same cardinalities. If you run it forever, I guess you can stop at depth n or something like that. You can stop at a bounded depth or finite depth. Okay. So as an example, okay. So obviously, if two graphs are isomorphic, then they are fractionally isomorphic. Now, can you give an example that the implication doesn't go the other way around? Well, for sure. So any two 7 regular graphs of the same cardinality are fractionally isomorphic, even though obviously they are not necessarily isomorphic, right? Because every vertex has 7 friends who have 7 friends of their own, who have all 7 friends of their own, and so on. So there is in all these partitions, there is only one non-trivial set. Okay. So that's one example. And by the way, it does relate. If you remember, there were these 2 examples, 2 kernels, which both did yield the Galton-Watson branching process with parameter 3.5. They were also 3.5. They were 3.5 regular. Okay. So that was the definition for finite graphs. Here, that's a bit more formal what I was saying. So we will remember this definition. I want a bijection between the vertex set. So normally you want bijection between the vertex set of G and vertex set of H, which preserves edges. That's what you want. What you want in classical isomorphism. Now you only want to preserve iterated degrees. Okay, and I will just call this bijection coupling because it moves me closer to this probabilistic setting. Okay, so as I said, there is actually there are fascinating equivalent definitions. One of them is we can take it as the starting one, the color refinement algorithm. An equivalent one is the number of copies in these graphs of each tree is the same. And by the way, this is somehow similar, like in some sense, counting trees and just making this connection now is a little bit. It smells a little bit like, well, the probability of generating trees in some Galton-Watson branching process, right? So the connection is not that straightforward, but there is indeed one. Okay. And the third one is a connection via matrices, via adjacency matrices, right? So the adjacency matrix of G and the adjacency matrix of H are related, by stochastic matrix P. Okay, and again, this is something from ordinary isomorphism, except in that case, P would have to be within a much more restricted class of matrices, namely permutation matrix. Okay, so again, this is a theory which was, which is really nice, and it has been worked out in the 90s. People were adding these equivalent relations, equivalent definitions, and okay. So now what Grebic and Rocha did recently is that they translated this concept of fractional isomorphism to well, graphons or kernels. It's not much more different. Okay, and so the paper is a complicated one. There is a number of analytic difficulties, like what is a counterpart of a bistochastic matrix and so on. But essentially, everything people knew about graphs, they could get a counterpart for kernels. Okay. Of course, previously the key notion that was used for fractional isomorphism was that of degree, and we do know what is degree in a kernel, right? That's this integral over this one-dimensional slice. Okay, so before this scalar refinement algorithm started with isolating vertices or separating between vertices of degree 0, degree 1, degree 2, degree 3. That was the first iteration. The second iteration was, the degree of each vertex was split into that part that goes into vertices of degree 0. Well, there's nothing, but vertices of degree 1, vertices of degree 2, vertices of degree 3. Now you do the same. You have to be careful. So, analysis or measure theory rather somehow plays a very heavy role here, because there are not a finite number of possible degree types, right? Not even necessarily a countable number of degree types. So, you can easily construct a kernel where every real number, say in the interval 0 to 5, is a degree. Okay, so whereas before this scalar refinement algorithm was based on comparing, in one graph and in the versus the other, in comparing cardinalities of these sets, now you have to express everything using the language of measure theory. Okay, so that's the counterpart. That's how the word cardinality translates to kernel as measure. Okay, okay. So, and I'm not giving definition. Okay. So, in particular, being fractionally isomorphic for two kernels means, when I simplify it a bit, that there is a measure preserving bijection between the spaces on which the two kernels live, which preserves the degrees, okay, and also preserves the degrees into sets of particular degree and so on. Okay, so there are two remarks here. First, I have simplified this explanation a bit. In particular, you do not have, so this is a remark for experts. I do not have, in general, a single measure preserving bijection which perfectly translates the degrees and iterations thereof. You rather have a sequence of better and better approximations. This is something you may know from the notion of weak isomorphism, which is a much better studied notion covered, for example, in Lovas's book, which amounts to two weakly isomorphic graphons having all the parameters you can think of the same. And while you would think, well, I must be able to bring the ground space of one to the ground space of the other in a single measure preserving bijection, you can only do that approximately with arbitrary precision. Okay, so that was the first remark. And the second remark, which is a remark which will not really, you will not really see its importance here, is that if I measure the degree, right? So for these pictures, what I was doing, I was only taking vertical slices. So everything, even though the kernels were defined on squares, somehow I took the x-axis as the reference axis where I was putting my root, and everything was done on the x-axis, and hence I was working with vertical slices, and that's how I computed degrees, right? Hence, you can come up with a reasonable notion of fractional isomorphisms even for kernels which are not symmetric. Okay, and that seems like a unnecessary generality for the Bolobash-Jansson-Riordan process, where you really did need the condition of symmetricity because you wanted to put the edge xy with the same probability as the edge yx. But as a matter of fact, for the uniform spanning tree, what we later do is at some point we start with a symmetric kernel and we transform it in a non-symmetric way. So we sort of need this generality later on. Okay. Okay. So now we know what fractional isomorphism of kernels is, and I hope I can hint proof of 1/2 of our main theorem. Okay, and it's really by far the easier part of the proof. Okay, so namely, I want to prove that if U and W are fractionally isomorphic, then this GWB of U and GWB of W have the same distribution. These branching processes have the same distribution. Okay. So what I have on the picture, I already started with. So I put down these two little purple squares. This is for sure going to be the two roots of my inhomogeneous branching processes. And I want to induct and show that the distribution of the number of offsprings, or the distribution of the first k levels for U and W, is the same if U and W have the same, are fractionally isomorphic. Okay? And obviously, I am going to use this coupling, this measure-preserving bijection, so which is indicated, so 3 particular points are indicated on the picture, right? Which preserves the degrees and preserves iterations of the degree. Okay. And again, the reality is a little bit more technical because such a measure-preserving bijection need not exist. It's not much of not a very deep issue. Okay. So I will use it to couple the choice of my root, right? So remember, in the first step, in GWB and GW of U and GWB of W, you're supposed to choose the placement of the root. So I'm going to choose the root for U and for W in a coupled way, right? So if I choose the root of U as my x1, then I could have used this measure preserving bijection, and I would get a uniform choice of the root for W, right? So I'm using the root for I call the root for U as x1, I call the root for W as y1, and automatically these two have the same degree, and much more, and iterations thereof. Okay, so now I should generate a random number of children of the root and the random number of children of U and of W, right? And because okay, so it should be Poisson of the degree of x1 in the case of U and of y1 in the case of W, and they are, by my construction, the same. So I'm choosing the number of children from the same distribution. So, okay, let's say I choose I generated 2 children for both of them at the same time. Okay. Now these 2 children, I marked one as green, one as gray. And when I put them, right, so now I'm using the definition of this inhomogeneous branching process, I should put these children back on the x-axis and generate children of their own. But these children were again generated in a coupled way, right? So in particular, you know, this green slice has, for example, the same integral. The green slice on U has the same integral that as the green slice for W. So both green children will have the same number of, well, the same distribution of children of their own. Okay, and I could, of course, I do iterate this. Okay, so what I arrived to is that really these two branching processes have the same distribution. Okay, so that was, and that finished this implication. Okay, so if the two kernels are fractionally isomorphic, then the two trees have the same branching distribution. So it's a pretty pedestrian proof, just making use of the definitions available. So the proof in the other direction is trickier. The main tool here is the Stone-Weierstrass theorem. I will not go into the detail, but the Stone-Weierstrass theorem allows you to induct on the depth of the trees you study, right? Recall that in general, the Stone-Weierstrass theorem goes from functions on a space to functions on the space of measures on that space. And this is exactly what is going on here, because we have this inductive structure. That's just the degrees, then measures on the degrees, then measures on the degrees, and so on. So that's, you know, that's how, you know, that's the measure theoretic counterpart to this color refinement algorithm. Okay, so that's the key tool for this direction, the Stone-Weierstrass theorem. Okay, and that was the end of the proof of the first main result, which was about, you know, characterizing when do two of these Bolobash-Jansson-Riordan inhomogeneous processes yield the same distribution. Okay, so now I will talk about the uniform spanning tree. Okay, and I'm a sort of combinatorialist myself, so I was, you know, when I studied, I was very familiar with Erdős-Renyi random graphs, but this model of uniform spanning tree is something I knew much less about. So for those of you who have the same background as me, let me just say a little bit about the model, which is more relevant for probabilists and people working in statistical mechanics. Okay, so I have a, you know, the model is pretty simple. I have a connected graph. I consider this set of all spanning trees of that graph. Okay, so by definition, that set is non-empty because the graph is connected. And now I put a uniform measure on the set. Okay. Now, you know, if you are seeing it for the first time, it may look as a bit ad hoc model. Why uniform spanning tree? Why not some uniform cycle double cover? Or I don't know. It turns out that there are really rich connections here to the theory of electrical networks. There is, for example, this obvious question: how do you even access such an object, right? Like, you can feel that UST of G, or the set T of G, the set of all spanning trees, will be, for most graphs, will be a very huge set. So how do you, for example, generate a uniform spanning tree algorithmically, even for a graph on, you know, 20 vertices, the complete graph on 20 vertices, right? How would you do that? And there are some beautiful algorithms which do play a key role in understanding, in studying USTs. So Alder's broader algorithm and Wilson's algorithm, which do allow you generate a uniform spanning tree very quickly. Okay. So people in statistical physics, they study uniform spanning trees mostly in 2 dimensions. So in 2 dimensions, you would have some, like maybe the 2-dimensional square grid, some other other 2-dimensional lattice. And this is a beautiful topic which has very rich connections. So, for example, there is this result of Lawler, Schramm, and Werner from 2003, which says that the UST Peano curve converges to SLE8. Okay. So when Wendell and Werner got a Fields Medal in 2006, this theorem is mentioned in his official citations. So I will not go into details. One of the reasons is that I'm definitely not an expert, but it's a beautiful topic which contributes substantially to this phenomenon of conformal invariance in random planar models. Okay. So, but I will not be, studying USTs on 2-dimensional grids, right? But rather on dense graphs. Okay. So, and the simplest theorem here is, and the first theorem in this setting is a theorem by Kolchin, reproven independently by Grimet in the 70s or 80s, and that goes as follows. So take a large complete graph and take a UST, uniform spanning tree, and look what is the structure of this uniform spanning tree when rooted at vertex 1. Of course, there is nothing special in the complete graph on vertex 1, just I'm fixing a vertex. Okay. And that the structure, so the number of neighbors of vertex 1 in this UST, the number of neighbors of each of these neighbors and so on, converges to the Galton-Watson branching for kernel constant 1, right? Well, it can't stop here. The sentence can't stop here, because if I stopped here, then it would say that for, this GWB of constant 1, that has a fairly good chance of, I think, like 36% of root not having a single child, right? So vertex number 1 not having a single child, and that of course can't happen in the UST, because for sure vertex number 1 must be connected. It's a spanning tree. It's not a disconnected structure. Spanning trees don't contain isolated vertices. So let me correct it to GWB of 1 conditioned on survival. Okay. So you take the Galton-Watson branching process with offspring distribution Poisson 1 and you condition it to survival. So this is a well-studied object, and there is a description which does not of this object which does not require any conditioning, and the description is as follows. So I try to indicate it on this picture on the right. You have the root. That's again the purple square, and from the root there is an infinite one-way infinite path. Okay. And now everyone on that path, including the root, you attach a Galton-Watson branching process with parameter 1. Okay, so what you are getting is, a random tree, which is for sure infinite because of this infinite path. And actually, that's the only infinite path you will find there, because all of these Galton-Watson branching processes, they are with parameter, they are going to go extinct almost surely, right? Each of them, and okay, there is just an countable number of them. Okay, so that's the local description which Colhin and Grimet described in the late 70s, early 80s. Okay. So now what I did several years back with Asaf Nachmias and Tuan Tran is that we generalized the theorem of Colhin and Grimet, which again allowed only to study uniform spanning trees on complete graphs, to arbitrary large dense graphs. Okay, and by the word dense, I mean, let's say graphs where the minimum degree is linear, then linear in terms of the order. Okay, so the vertex of every vertex has degree at least 0.01 times n. Okay, so this is a setting which is very natural to a theory developed by Lovász and his co-authors, most notably Box, Childs, Sors, Szegedy, and Vesztergombi. That's the theory of dense graph limits. And this theory provides objects called graphons. Well, what are graphons? They are just symmetric kernels with an extra assumption that they are bounded by 1. Okay, so that's the objects they work with. And there is a notion of a graph sequence converging to graphons. Okay, and that theory has led to many breakthroughs in extremal graph theory, and actually also in the theory of random graphs. Okay, so when usually a theorem connecting, a theorem in graph limit starts as like our theorem. Suppose that you have a sequence of graphs that converge to a graphon, again in this usual notion which is called cut distance convergence. Okay, now in our theorem I added the word connected, because when we want to study USTs, we just want connected graphs. There is no meaningful theorem otherwise. Okay. And suppose, let's say that these graphs have linear minimum degrees. Then what we can describe, the uniform spanning tree in Gn around a randomly chosen vertex, it converges to a certain process which I call USTW. Okay. And we do, so there is a certain branching process which a second branching process derived from a kernel or from a graphon. The first one was this inhomogeneous Galton-Watson branching process, which was also parameterized by a kernel. Now I have this process which is parameterized by a graphon, which is a particular kernel. So I'm not going to define this USTW. There is a definition which again involves some Poisson point process, but I will only show you an example. Okay, so suppose that the sequence of graphs you have is complete unbalanced bipartite graphs. So k n quarter, 3 n quarter. Okay, so that's, these are these finite graphs on which we would like to study USTs. Okay, now, what the graph limit theory tells you is that this sequence converges to a graphon, which is as follows. So, there are zeros, there are 2 0 blocks on the main diagonal. The first one is smaller, measure or side length 0.25, and the second one is bigger, the side length 0.75, and the off diagonal entries are 1. Okay, and then using the definition or the construction in our paper with Asaf Nachmias and Tuan Tran, we can tell you that the local structure of the uniform spanning tree will be approximately like, well, take the root, of course there will be the root, take a one-way infinite path, and now what you do is you alternate including these green and pink Galton-Watson trees. Okay, either starting with the green one, or starting with at the root, or starting with the pink one at the root, right? Where these two variants appear in ratio 0.25 to 0.75. And what the green variant is well, this alternating Galton-Watson branching, where on even levels you have 3 offspring, so it's Poisson 3, and on the odd levels you have Poisson 0.333, and the pink one is on the even levels you have Poisson 0.333, and on the even levels you have Poisson 3. Okay, so that's that's just an example. That's just an example of this Galton-Watson branching tree. There is always in that construction, no matter what graphon you have, you always have this one-way infinite path, and then there is a way how to append some inhomogeneous processes on each vertex, including the root of that path. Okay, so that's what that was previous work where we describe how does the uniform spanning tree seen from a uniformly random vertex look like in terms of the limiting graphon. And now in the current work, what we did is, again, we characterized when are the structures of these branching processes UST the same depending on the graphon in question. Okay, so if I just copy the theorem, our main theorem 1, then that went like as follows. So USTU and USTW, I have two graphons U and W, and let's say they are connected. That's you have to be more careful in the disconnected case. Have the same distribution of these trees which contain this one-way infinite path and so on. If and only if, okay, I copied that from our first theorem, U and W are fractionally isomorphic. That's maybe what I would like to see or get, except it's not true. So recall, this result of Grimet and Kolchin said, well, when U is the constant 1 graphon, which is what you get as a limit of complete graphs, you get this Galton-Watson branching process conditioned on survival, which is equivalent to this construction. You have the one-way infinite path, and you attach these critical Galton-Watson branching processes, Poisson 1. And you can easily see that you do get the same branching process for any other constant. Okay, so you would have to check the definition or the construction that I have in the paper with Nachmias and Tran. But when W is, say, a constant 0.3 graphon, which you can get if your host graphs, the graphs that host your uniform spanning trees, are, for example, a sequence of quasi-random graphs of edge density converging to 0.3. Then the branching, the branching process UST is the same. Right? It's sort of intuitive because you know, the UST doesn't really know whether it was chosen from a complete graph or rather from a quasi-random graph of a smaller density, because it's going to take a negligible, it's going to use a negligible amount of edges anyway, right? So, okay. So what I did, what this picture shows, is that the theorem, as was stated above, can't be true because I have two graphons which are for sure not fractionally isomorphic. One of them has every degree 1, one of them has every degree 0.3. So, you know, this measure theoretic counterpart of the color refinement algorithm would distinguish these two already on depth 1. And yet they yield the same USTs. Okay, so the correction is that U and W are what we call affinely fractionally isomorphic, meaning that I can multiply one of these graphons by a positive constant to get something which is fractionally isomorphic to the other, right? So that's our main theorem, that there are two operations which, you know, again, if you remember the first theorem, I showed the sort of the easy direction, which was if two graphons are fractionally isomorphic, then these Bolobash-Jansson-Riordan branching processes for both of them yield the same distribution of rooted trees. Here, in this easy direction, there would be two steps. Well, if two graphons are fractionally isomorphic, then these USTs are the same. And if one graphon is a multiple of another, again, the UST is the same. So both, you know, both parts of this direction, of this implication is trivial to check. Maybe let me say, if you want to go in the other direction, so if UST of U is the same as the UST of W, it's actually quite hard. So, you know, this direction in main theorem 2 is much, much harder than main direction in theorem 1. Okay, and with that, let me stop.